how to cheat the second law of thermodynamics. Now let's talk about this, at least to see where we get to. If we can't get anywhere with this idea, then we'll get back to the boring stuff. Okay, transition state theory. All right, so we were talking this morning, the first part of the lecture, about how to cheat second law of thermodynamics. We want to bypass heat. Okay. So for those of you who are, I don't know how to do this stuff. Okay, I'm just throwing a random model on the board. It's probably not the right way of doing it. But let me just give it a background. Okay, the reason why we do combustion, of course, is we want to take a chemical energy that's an enthalpy in the field, reacting this with oxygen, producing carbon dioxide, that generates heat. Heat is used to raise the temperature of the products. Then you use this energy in the product to transform into work. Because of a chemical to thermal, then to work. Chemical energy to thermal energy, then to work, you must pay a price in between. And that's bound by second law of thermodynamics. Now, one way to get around with the heat problem, the molecules are moving about. They can either move all in one direction, or they can move randomly, right? After all, enthalpy released from combustion. You don't care what at the end it goes into kinetic energy. You just have to guide this kinetic energy in one certain direction. Now we all agree with that. So here's the model to start. I'm very sure this is not right. I just thought about it briefly over the break to structure this. Suppose I have reactants on this side. The thing I have to do work on is on the other side. Okay? This is the room temperature. This is also at the room temperature. Alrighty? Except for that over here at the room temperature, I have a sonic flow. But its temperature is room temperature. So I can have random motion over the molecule, you supply reactants, right? I have a surface over here. You're going to have surface reaction, catalytic reaction. Final product being carbon dioxide and water. All right. If you assume that you're going to be able to find something so that the thermal energy in carbon dioxide and the water do not get transferred into the structure itself, carbon dioxide and water shall return this kinetic energy. You will then shape the potential energy of the surface. That I can assure you, there are people who know how to do it. Let's not worry about this problem. In that way that the heat released from the combustion reaction on the surface turn carbon dioxide and the water into their kinetic energy, and you shape the potential energy so that they can only move in one direction, through a horn or through the channel. And you play the game at an end such that when you dissolve this highly excited carbon dioxide and water molecule, they can only move in one direction. Now from propulsion standpoint, you're going to be able to have a gas turbine engine that doesn't have fan blades. You react here, gives you the thrust over there. Comments? I have to stay that far. Maybe I'm not. You don't have to follow me. Can we do that? Any alternative ideas?
So this one works reverse thin layer on the surface.
Very thin layer, one monolayer of absorbing.
Viscosity.
I'm sorry?
You will have viscous effect.
You would have viscous effect at the molecular level. The viscous effect essentially comes from well hopping.
But for that, we can use superconducting material or something.
Which component are we going to talk about first? Or we should stay at this model for about 5 minutes before we know how to break this problem down into smaller pieces, examine the validity of various assumptions we made in this model. Thoughts? Ideas? I'm not doing the wrong thing. I gave you something that's too constrained. You want to forget about this model and start from new? Yeah, go ahead.
I don't have any idea, but it seems like this model you are limited to surface friction and as well as the amount of surface that you have. It seems like pretty impractical for me to actually achieve it.
Okay, so let's say the mean free path of a gas, let's make it a few tenths of a nanometer. Okay, there's no problem for me now to generate a structure with a diameter over here of the order of 10 nanometers. So density is not an issue. Okay, density isn't an issue. I can pack energy density high enough with this model. Remember the rule of thumb in science is to prove a theory wrong. That's exactly what you're doing. That's good. Finding ways to see this model doesn't work. And if you can't find any argument to disprove it, then this is worthy to work on. No? Any other thoughts?
In this model, you told me you can need heat release before.
Yeah.
So just to regulate the motion, will give you.
But inherently, by thermodynamic first law, the momentum or the kinetic energy of the gas molecule leaving the channel must come from the enthalpy release itself.
You take the energy from the random motion, just regulate.
That's right. This is precisely the regulating the random motion into direct motion down the channel.
So having low temperature exit.
I'm sorry?
You have a lower temperature.
I have a low temperature exit, but there's a high speed.
So
This you all know, right?
this will violate the second law.
I'm sorry?
It will violate the second law.
Do I violate the second law? Right. Let's start from that question first. Do I violate the second law of thermodynamics?
You don't. If you put in work into the system.
I'm sorry?
You have to put in work into the system not to violate the second law.
Mm-hmm.
Which you will have to in order to combustion process.
I'm sorry?
Are you constrained to combustion? I mean,
What exactly happens when you break the chemical bonds? You're breaking a few bonds and forming a few bonds. To do that, you need to have an energy source from somewhere. Just because you have you have surface catalysis doesn't mean you can break bonds and form bonds without any penalty.
Okay. Well, let's assume for the time being I can develop a catalyst that can do low temperature oxidation. Okay? My end product is carbon dioxide and water. I don't know if you played with platinum nanoparticles. You take a pinch of platinum nanoparticle, dump into ethanol, you got fire. Low temperature catalysts exist. Okay? Obviously you don't want to use platinum, but there are plenty of catalysts that we can play with. So let's assume for the time being that low temperature combustion is feasible, catalytically. And of course, if you produce carbon dioxide and water, you must get chemical enthalpy release. And this chemical enthalpy release, if you don't play with it, then it must turn itself into heat, raising the temperature of the product. Okay? This thing you know, right? If I start from a compressed hot gas, run this through ideally isentropic expansion, What I'm doing there is turning random heat, thermal energy, into molecular motion guided in one direction, right? Temperature drop, but the velocity increase in one direction. All right, this is just simply you ask the kids in the kindergarten room, say, well, stop random motion, walk in the line to the library. Question is, how do we do this at a molecular level, right after the reaction?
It's a material issue then.
I'm sorry?
It's a material issue then.
It is a materials issue. You're correct. But as a material issue, it's also a potential energy issue. Okay? You say I roll a ball down the hill. You can do this randomly, or you can dig a channel, let the ball to run only in one direction. Reaction are following potential energy surface, right? Potential energy surface is what guides it. So why can't you do this at a molecular level?
Well, suppose you can make a stem tube to guide the motion in one direction.
Mm-hmm.
So what can prevent the molecules coming back from the other?
What prevents it coming back from the other direction?
If you go for this direction too.
Okay, let's take this model. Suppose now I have an array of nanoscale propulsion device, and all the gas just goes in that way.
But you have gas and acid try to come back.
No, but if you can make a nozzle out of it and choke it after the
You always
nanotube.
have molecules moving back.
No, I agree, but if it's choked, then it can come back. So put a nanotube kind of cylinder so that you direct it straight and then have a nozzle out of it.
Here again, suppose you get a stem tube. So if the molecule comes whatever end, it will just go straight through it and then move normal to the wall. So it can go this side or this side. So the channel itself is just a channel, carry it to normal direction, so the motion will be one dimensional. So if you have high velocity molecule coming from this side, low velocity coming from it, you still have collisions. And this collision will bounce this back or force. So if this one dimensional bouncing back, you still
If you have a
Well,
low
it's
pressure on the
more
exit
like,
side, it's free momentum flow.
It's more like starting
Let's
of
see,
a
you're moving this
nozzle.
direction.
Starting
Looks like,
from-
but if you sometimes moving slower, trying to go back, you still have this bouncing, right?
So his point is this: you're not ejecting this molecular flow or gas flow at a macroscopic scale into a vacuum.
no, but
Vacuum would be fine. If you
Vacuum would be fine, yes.
no, but it's the same problem as starting of a nozzle, right? That's how it's a starting nozzle problem.
But why can't it
It's
enter
different.
the same way?
I mean, it's
the way.
I'm sorry?
It could come out the same way it entered in. It should not even go through the nozzle because the space outside is much bigger than the nozzle.
Oh, wait, one at a time, one at a time. Yes, sir. I'm sorry?
I'm saying the size of the nozzle is pretty thin and the space from which it is coming in is pretty big. Entropically, why would it want to go into a smaller channel than to where it came from already?
Why would it go not reacting with this surface is possible? The question is that why doesn't go randomly, fly off on the surface?
Because
Okay.
entropically, the space in which it can go into is much bigger than the space in which you want it to go into. So there's an entropic barrier already there which will prevent it from going into the nozzle in the first place.
What we are saying is, if you wanted to prevent it to fly off, right after the reaction, you have to design another part of a potential energy. Let's suppose you have a reaction, reactants, product, right? This is the product, you form it with that much enthalpy produced. It's jigglish. It wants to leave the surface, and it shall leave the surface randomly. What if I design another well so that it tends to go over here? Do we have any more potential energy parts beyond the carbon dioxide and the water that we can allow it to go downhill? Yeah.
One problem. How do you, so if you want to gradually stronger attractive potential
Correct.
Along the length of the tube.
Mhm.
So that's how you move them. But to release them, you need to have a repulsive potential at the tip.
Mhm. You don't have to have repulsive potential. You just have to have kinetic energy to escape the potential energy well. They're already moving very fast, right? The way how you want to structure this is that even though you are locking the molecule on the surface, that molecule has its own kinetic energy. For you to go down that way, it must be speed up. If you don't speed it up, you're to random motion. Speeding it up requires you to have a downhill potential energy surface, right? That parting is inherently consistent with each other.
So we have to design a potential surface for every reaction, the solid of reaction.
You need to design a potential energy for the catalytic part of the reaction only. If you can get complete combustion, let's say for the time being, assume you're going to form carbon dioxide and water, the remaining part of the surface can be the same. Or maybe now we can expand it. Why can't you have reaction going down? You have formaldehyde here, you have CO here, you have CO2 here. You speed up a mass sequentially. Those are, you're expanding the initial concept. I'm just asking, what is wrong with this model? What laws am I violating? A lot of this argument is correct, okay? I'm sorry.
You're still following carbon cycle.
Which part?
The exit part.
The exit part, I'm still following the Carnot cycle.
It's not closed.
I'm sorry?
You're not running a cycle.
I'm not running a cycle. You got it. Wouldn't you agree? This, at least, let's not talking about tossing on any space propulsion. If you can do something like that, you will be able to do it, right? So your problem is not important now. The question is, when you eject into a finite atmosphere, indeed you get problems over there. So there's a mini Carnot issue involved there, involving the randomization of this flow quickly as it ejects from end of the nozzle. But you do save quite a bit of in between, because if you look at turbine engine, you do turn chemical energy into heat and then use the heat to do expansion and drive the turbine. You don't have that part anymore. All right, come on guys, shoot at it.
It sounds like a perpetual motion machine which can run by itself without any.
Oh, you're constantly providing the current, right?
You could take the work from the output and you can provide it. I mean, like, at some level, it sounds like a perpetual motion machine.
I think for space propulsion, ISP will be an issue of what we are looking at. Because I don't know if catalysts exist for all kinds of space propellants. Storage, whatever, all the other things.
All right, as I see you all getting depressed, we're going nowhere. Let's put this up here. One of the things that I will tell you is, if you ask my gut feeling right now, something is wrong with this model. I don't know what. All right. So my suggestion is this: take this thing, play with it, and from time to time just think about it. You find something wrong and against a certain law, let me know. But if you can't find it, some of you will come back next year. If you still cannot find what's wrong with this model, well, maybe this is something we'll have to work on. Okay? All right, we'll stop here. We'll go back to the transition state theory. So the other part of the reason I wanted you to have this discussion is that in the end, reaction processes is always about collision. You show, do collision on the potential energy surface. And it is the collision and the potential energy that dictates the rate and outcome. That is the nature of the product of a reaction process. Okay. So that's how the potential energy is intrinsically related to the potential energy of an reaction itself. Now, I don't intend to go through this lengthy discussion about transition state theory, but rather just to give you an idea. Okay. The postulate of transition state theory is there exists a critical geometry, that beyond this critical geometry there shall be no return. Took you effort to climb up the potential energy ladder, but once you go over it, you're going to slide down. These two molecules are never going to see each other ever again. All right? This is a model. There have been many instances that it can be proved to be wrong. That is, potential energy. We are describing this process in a very simplified form. You have one reaction coordinate. But potential energy can be infinitely complex. Imagine you go for a hike in the mountains, the trails and so on. They can be interlinked. So recrossing does occur. You go over the barrier, you come back through other paths, and then you recross the barrier back. Okay. If you were at the first CEFRC summer school, Professor Dr. Klippenstein talked about was exactly that. Various recrossing dynamics. Okay. For now, we will follow the rule rather than exception. We take AB colliding with C. I shall form this transition state complex. Its nature is it's transient, and its concentration can be approximated by looking at the equilibrium constant of its formation. And obviously, its population is determined by the concentration of the reactants itself. The more reactants you're going to have, the more likely you're going to form this complex. Okay. Then the overall rate constant for this reaction is essentially this equilibrium constant for the production of this transition state, multiplied by the rate of this transition state hopping over that to the other side of the barrier. Okay. So this is the equilibrium constant, gives you mole per cc unit. This is the constant that gives you the time unit. Okay. So the remaining problem is about how do you determine this equilibrium constant and this time constant for transition. Once the condition is right, remember, you ask the question, what about other motion? The condition is right does not mean the transition will take place. You still have to take a few tries for it to do that. So the way how we analyze the dynamics of this transition state, you can assume it's in equilibrium, or you can assume this in steady state. Either way, you get the same result. I'll pass through this analysis. And why did I jumping this? I don't even remember why I would do this. Okay, the equilibrium constant. Okay, we know now the total observable rate constant is this equilibrium constant multiplied by some sort of a time frequency factor. So let's look at equilibrium constant first. The equilibrium constant is basically partition function. Okay, and if you look at the Gibbs free energy, it is defined as H minus Ts. You can expand it, regroup into internal energy, temperature times entropy, and some sort of a P times V that refers to the work component of that. So still mechanically, you can replace this internal energy by the mean energy, minus KT, that's the entropy expression, if you recall we introduced this yesterday, and you have the PV term. You regroup this whole thing, and what you find is this is basically negative KT times log Q, where Q is the partition function. Okay? And long story short, at the end, you should find is the molar Gibbs energy is directly related to the molecular partition function in this form. Okay? I don't want to explain where the n comes from. It's all fairly obvious. And if that's the case, the molecular partition function, we have the expression for it already. You have the translational part. You have the vibration, rotation, electronic part. Okay? So Gibbs free energy is basically natural log of molecular partition function multiplied by RU, that's a gas constant, times temperature. Through that, you can define equilibrium constant for that we wish to derive as the exponential of Gibbs free energy of reaction. And in this case, the Gibbs free energy is between the top of the hill, the saddle point, and the lower end, that's the reactant. Okay? Plug in the expression for molecular partition function. The equilibrium constant is basically the partition function ratio, where n naught is the Avogadro number. So that's the constant that's not important. Okay. So a little more over here. Let me just skip all this. It's not important. Let me give it a what do we have neglected here? Oh, I have to talk about this. Over here. Okay. So this is the molecular partition function ratio that determines the equilibrium constant. Okay. We need to do a couple more things before we can get to where we want to get to. Okay. The first is we wanted to express the enthalpy of reaction as a function of electronic energy corrected by the 0 point of vibrational energy. So you take the forward barrier, subtract reverse barrier, subtract the forward barrier, corrected by the 0 point energy of the reactant and the product. That gives you reaction enthalpy. What I want to try to get at it is that you have an electronic partition function that you need to worry about. It is the electronic partition function that gave rise to the exponential term of reaction energy barrier. So relative between the transition state and the reactants, you're not comparing them on the same basis. For that, the partition function needs to account for this energy barrier. The point here is this derivation is intrinsic. It says that electronic partition function for the ground state is given as some sort of value, that is for the reactants. Okay? Yet if you reference this to the transition state, the energy barrier must come out. Okay? The net result is we have to consider the vibrational contribution to the partition function. You need to combine this with the electronic partition function, and once you reorganize it, you get a somewhat a new form of this partition function for the vibration, but then an energy term that's got grouped with vibrational 0 point energy that got grouped into the original electronic energy barrier. All right? I know you won't understand this, but don't worry. I'm going too fast here. In doing so, what you get is a partition function ratio for two species is basically related to an exponential function over here that's related to reaction enthalpy, and you just need to restructure the vibrational partition function and call it a Q prime. And plug in there, you get this expression. Long story short, now the equilibrium constant shall be expressed by this modified partition function of the transition state divided by the original partition function for the reactant AB, multiply that by the second reactant, that's C. But the reaction enthalpy naturally pops out at the end. That's what this whole exercise is about. Combining the vibrational partition function and the electronic partition function, reorganize it mathematically, such that the reaction enthalpy pops out as an exponential term, then the remaining goes into the front. And this front partition function does not contain the 0-point energy contribution. Alrighty? Then all right. So we've talked about so far that's Kp. And this for transition state theory, you're taking two reactants making the transition state. So Kc and Kp must not be the same. Therefore, the correction is from Kp, you have to multiply this by universal gas constant times temperature. You rework this into the definition into Kp. In other words, you divide both the numerator and denominator by RUT for each term. Okay? And from there, you define now nRUT. Why does it turn into V? Oh, I see. This is written into the Kc where the reference pressure is 1 atmosphere. So nRUT is basically the standard volume. And what you get is equilibrium constant that is equal to this new definition of the partition function ratios. And again, you have the reaction enthalpy popping out at the end. Okay. And the result is that you can define this molar partition function called Z for each species involved. Transition state and the two reactants. You have Q prime now divided by standard volume, and that's given by this expression. You have the original contribution from rotation, electronic. Now this part is purely involving the degeneracy of the electrons. You have the translational part. Then at the end, the equilibrium constant is a modified volumetric partition function ratio of the transition state divided by that of a reactant. I think I have the AB missing somewhere here. And you have the exponential term due to reaction enthalpy. All right. Put this in the form of equilibrium constant for the transition state. You find that this to be X DAC, which represented this transition state, divided by the reactants, product reactants. Then the reaction enthalpy is replaced by the energy barrier for the forward reaction. And this E represents electronic energy difference plus 0 point. Okay. Then the transition state theory, rate constant for the time being, the equilibrium constant may be replaced by this term. So now, what about the KDAC? KDAC describes the rate at which the transition state crosses this dividing point down to the other side of the potential surface. And the way how we describe this problem is in fact quite simple. First of all, if you look at this motion, all what you have to figure out is a velocity, a mean velocity for this translation process to take place. And you should divide this by the length scale of the reaction process. Okay? And the V bar is the mean molecular speed. And that's kT over 2 pi mu. We talked about this expression earlier. What is the length? Even I'm lost. Where did this thing go? Okay, all right. So the V bar is the mean velocity of the gas. And you plug this into this expression. What you're going to get is for this, why does this translational partition function got introduced? I'm sorry?
To find out the length scale, so particular box to find out the length scale.
Never mind. let me just jump through the result. I forgot how this derivation is done. It's all in the note, but let me just go through the end. Well, it turns out this time scale that we're interested in is simply kt over h. All right, long story short, let me not derive this. I forgot altogether. Anyhow, so this motion essentially is a kt. It's related to, let me explain this. Kt represents translational energy, correct? And you're turning into quantum mechanical form, so the h times mu is the wavelength, the energy due to a wave. So h times mu, that's the frequency. Okay? You take the kinetic energy divided by h gives you a frequency of a motion along one-dimensional geometry, along that reaction coordinate. And that's where the kt over h basically gave you the kdec. Okay, that's the time scale for this reaction. Then this will give rise to the transition state theory. That's this expression. You have the translational motion over here. You have the partition function of the transition state divided by the same for the reactants. Okay? Then you have the reaction energy barrier. All right? And the result is that in general, rate constant expressed by the transition state theory has the natural temperature dependence in the A factor. Moreover, if you look at a partition function, there are additional temperature factors in this ratio. So for metathesis reaction, it can be proven that you have one T dependence here, you have another T dependence there. So if you look at a hydrogen abstraction reaction, typically you'll find a temperature exponent around the 2. Around the 2. So you have an A factor, T to the power of 2, then you follow this by a pseudo energy barrier. Okay. Now, you're going to have to make other corrections. This expression is not always correct. The expression that we always needed to consider is this transmission coefficient. Is it called? It's a transmission coefficient that is not every, well, that's the frustrating point of all this basic theory. The basic theory is once this is all done, you realize any non-ideality has to go to a factor that corrects it. And this is a transmission coefficient ranging with its value from 0 to unity. Okay? And you can have a whole universe of this rate constant, except the fact that now transition state theory defines the upper limit of a bimolecular metathesis reaction. Okay.
I have a question.
Sure.
You have a statement there saying that it frequently assumes a value of 1, the transmission coefficient.
Yeah.
Why are you saying it assumes the value of 1?
Oh, when it's 1,
Where's the assumption?
this has to do with molecular collision orientation that you're not considering. For small molecules, car is very close to unity. For very large molecules, if you run into the problem, suppose you are trying to react a methyl chloride. You have a large ring structure. You have a methyl sticking on the top. You have an orientation problem because for any molecule coming to react, if I were to abstract this hydrogen atom, my orientation must be correct. Transition state theory does not account for that. For example, that's one correction factor you have to make. General rule of thumb is the smaller the molecules you are dealing with, the closer it is for the transmission coefficient to be unity. Whereas if you go to large molecule reaction, the transition state theory can fall apart. And that is the reason why this value ranges from 0 to 1. Okay, does that explain? So if you look at a reaction between OH plus H2, this theory works very well. You go to something like N.AKM, well, if it saves us because the hydrogen abstraction can occur on every possible hydrogen atom. In the case of methyl, say, chlorine, you have a big problem because the bond energy in the CH, okay, is very different from bond energy in the aromatic. Therefore, the rates are very different. And if you want to specifically abstract this hydrogen atom, this falls apart. Already.
Then you have to determine a transmission.
I'm sorry?
Then you have to calculate the transmission.
Then you have to calculate transmission coefficient, yeah.
For your break.
And then, in reality, this isn't that bad. The transmission coefficient won't be that low. Okay? I will leave this on the side. I have 50 minutes left, so I skip quantum tunneling and go to the next one. I should have known this will never go well if I have to do transition state theory and RRKM theory in one day. Anyhow, all right. Now, let's talk about other type of reaction, unimolecular reaction. Okay. Now, all this involves a interplay of different types of potential energy surface. Okay. If you look at a unimolecular dissociation reaction, molecules split into two radical species. Its potential energy is rather simple. You follow the reaction coordinate, short range repulsive, long range attractive, and you just have to pull the two atoms or molecules, radicals apart. And that's unimolecular dissociation. Okay? The reverse is a radical-radical recombination. Usually does not have an energy barrier. All right. Now, if you look at an elimination reaction, that is, I have a radical to start. And as I dissociate this radical, I'm going to find the reverse reaction to be that of a molecule with a radical. Usually, that process is associated with a finite barrier. This process, from the unimolecular reaction standpoint, is called elimination, eliminating that radical species. Okay. When you do isomerization, for example, primary N-propyl radical and the secondary isopropyl radical can undergo mutual isomerization, involving hydrogen atom hopping from the middle carbon to the two end carbon, or vice versa. The potential energy surface is typically represented along the reaction coordinate is typically represented by two wells separated by a barrier. Then going into further, you can also have H plus O2. With a small barrier, it shall form the HO2 molecule. All right? The HO2 molecule over here can be stabilized into the well. It's vibrationally excited. You shoot a cold molecule at it, remove this kinetic energy, internal vibrational energy, you'll get stuck. Or if you leave this excited species out there for long enough time, then it can either dissociate back to H plus O2 or dissociate into O plus OH on this side. The main chain branching reaction, H plus O2, follows this type of potential energy surface. So is a CO plus OH. CO added to OH, producing this HOCO radical, HOCO, which can eliminate a hydrogen atom to form CO2 plus H. Okay. This full potential energy surface shares one thing in common. It all involves certain dissociation of the chemical bond, whether from here or from there or from there. And if you notice, this potential energy is a superposition of this or that, split them into two. That is, over here, as long as you can allow this additional dissociation to occur, then you can bend it back down. So the nature of this potential energy surface are the same. Are we okay with that? Okay. So how do you deal with this? Now, let me specifically talk about a chemically activated reaction. Take one example. Two methyl radicals come together. Initially, each has its own translational energy. So they bang into each other. If they bang into each other, this translational energy can get into other modes of vibration, into the 6CH stretch. So you collide them together, the 6CH gets excited. Okay? If you bang into each other, not orient them right, it can go to mutual rotation. So those modes of vibration tentatively hold this potential kinetic energy, translational kinetic energy, into this complex. It is for that reason those complexes would have finite lifetime. In vacuum, statistically, all of the energy eventually can be channeled back into the CC bound oscillation after a certain time. So if you leave it there, the ultimate outcome of this reaction is you fly apart again. Not always so. You realize that, hey, what about, I said earlier, that you have this two moiety coming into each other. Some of this translational energy gone into vibration in the carbon-hydrogen bond, right? What if all of this energy comes in and all of this energy goes into the carbon-hydrogen bond? Then I shall be able to collide them, popping out this hydrogen atom. That process is chemical activation. Okay? What are competing with that process? There are a couple. Coming in, going away. Coming in with sufficient lifetime so that a cold nitrogen molecule comes, colliding with it, removing the internal energy, vibration energy from it. And in doing so, stabilizing this into an ethene molecule. So long story short, what really is happening is we have to consider a potential energy surface that looks like this. Methyl plus methyl, both being radical, so the combination of the two methyl radical is barrierless. Okay? Coming in, can it go out to form ethyl plus hydrogen? Inside, you have ethene. The argument is that since the total energy is conserved, methyl-methyl recombination should initially produce this excited complex whose internal energy sits above both exit well, exit channel. Unless you remove this energy by collision with a certain frequency associated with it, then this thing must eventually go back out or go across over here. So this potential energy is the opposite of the metathesis reaction. You flip this around, that becomes a metathesis reaction. Then it follows that even though the combination part of the dynamics is described roughly by transition state theory, roughly only, we need to now, in addition, consider the dynamics of a conditional stabilization. And this dynamics, well, I'm not following myself right now. The dynamics of stabilization is associated with the excitation itself. Okay? If you think about this problem in reverse, if I start with an ethylene molecule in a system, itself establish a Boltzmann equilibrium so that its internal energy distribution is exponential. Okay? You have some sort of a threshold energy above which you are poking against above this barrier. So this is the reactive population. Okay. During the stabilization process, you start from here. Collision brings it back. But the collision also brings the molecule, energize it, purely statistical. So the de-excitation and the excitation itself is basically Boltzmann statistic on its own. And that follows microscopic reversibility. Excitation, de-excitation described entirely by the Boltzmann energy distribution itself. It is for that reason, from the standpoint of statistical mechanics, the stabilization and excitation is of the same phenomenon. In any case, it's unlikely you're going to be able to stabilize this molecule in one step. You have to do this in many steps. And as you do this many steps, you may have 3 collisions leads to down energy transition. The next one you're going to excite it, followed by another 2 down, another 1 up, so on and so forth. So the dynamics of a collision in this process is identical. Okay? It's just overall from energy, where the energy goes, it's in following 2 separate directions. Anyhow, so intrinsically, the stabilization is the same as excitation from Boltzmann statistics. The result is that we just need to consider this problem from one end. The other part, we handle this by equilibrium constant. And we shall do this analysis from the standpoint of a unimolecular dissociation, starting from excitation. We discussed the unimolecular reaction rate theory 2 days ago, okay, following the Lindemann mechanism. All right. We said that this A is a molecule that's ethylene sitting down the well. It's constantly doing collisional energy transfer by colliding with other molecules in the system. I'm going to always get a a finite population of excited molecule, A star, capable of breaking the bonds, either the carbon-carbon bond or the carbon-hydrogen bond. Okay? While you're doing this fast up and down transition, occasionally you're going to get a structure that's just right. All right? Not every molecule having internal energy at this level is capable of dissociation. Only some of them. Why is it? It all depends on how this energy is partitioned. You want to have all of this energy if you're only at this level. You want to make sure that the vibrational quantum number for every other normal mode vibration to be 0, with the exception of this reaction coordinate normal mode vibration. And only that can break the carbon-carbon apart. Okay? If you go higher in energy, you have a little bit more space to play with. But nonetheless, it shows that not every excited species is capable of undergoing the transition moving to products. And this whole thing is statistical. Okay. So then you ask the question, let me just skip all this. What is it? The consequence of this fact is that is that if you will be able to know the total number of possible energy state available for going out through this channel, statistically, you have that many excited molecules, only that proportion is able to react. You take that total energy states divided by the original state, possible number of state. You get a fraction of molecule that are capable of reacting. And that's the RRKM theory. Now, let me get back to why we need to do that. We explained this whole thing on the basis of Lindemann theory, if you remember. The Lindemann theory states that the unimolecular reaction is described by a low pressure limit and a high pressure limit, such that the rate constant shall vary as a function of pressure and a given temperature. At high pressure is a constant, at low pressure is proportional to the pressure. Okay? That theory is not complete because it does not quite consider the detailed collision dynamics. The result is that you're going to find a large discrepancy between the actually measured rate constant and the Lindemann approximation. All right. Looking at this actual example, we are looking at a rate coefficient of reaction that's acetylene reacting with hydrogen ion. The reverse is vinyl dissociating into acetylene plus H atom. If you use the Lindemann theory, all what you need to know is the high pressure limit rate constant and the low pressure limit rate constant. You can get that by doing experiment at a very high pressure and at a very low pressure. Okay? With these two rate constant, by Lindemann theory, you can construct the unimolecular reaction rate constant in a fall-off region. It turns out that back in about 1950s and the 60s, we realized that the actual rate constant measured in the pressure fall-off region is in fact substantially lower than the Lindemann expression. So a better theory needs to be developed to account for this phenomenon. And that theory is the RRKM theory. Now, in the Lindemann description, it says that phenomenologically, any A molecule, when you get to A star, this A star is undefined, as a matter of fact. You can have an excited molecule with energy that's right here, or you can have excited molecule with energy over there, relative to the bottom of the well. Obviously, this molecule with that much internal vibration of energy must have a different frequency factor for it to transit to product. In general, this rate constant must be substantially smaller than that rate constant. Why is it? For the simple reason that this molecule has a lower vibration of energy than that one. Smaller vibration energy gave the less chance to have all of this necessary energy to get into this particular normal mode, to separate that bond. Okay? And if you go to that high energy state, it gives you better probability. It follows that the nature of A star needs to be precisely defined before you can come up with an accurate description for this rate constant. The way how you do that is getting into an energy-dependent A star. You are saying that depending on the internal energy, I shall get a different rate constant. All right. Then this is what's called the microcanonical process. Is you're holding the energy constant. Thermal property is the result of an integral of this energy-dependent property weighed over the Boltzmann distribution. You integrate it over the entire energy range, you get a thermally, you get observable, you get rate constant that's thermally observable. So let me explain this, the concept behind it. Okay. A unimolecular reaction rate constant that can be observed under given temperature is the result of the many microcanonical rate constant, energy dependent, not temperature dependent. Each particular vibrational energy level, you should get a particular microcanonical rate constant. But if you assume this whole thing is in Boltzmann equilibrium, then you have this Boltzmann distribution factor there. That is, if I take, without doing a sum, without multiplying this by the microcanonical rate constant, Fe over sum Fe is the Boltzmann distribution itself. You then weigh each rate constant at energy E sub I by the population at this energy level. Sum it over, what you get is unimolecular rate constant. So this concept in itself is identical to how we determine the internal energy from statistical mechanical theory. So is pressure, so is entropy, so is everything else. So now let's talk about RRKM theory. The RRKM theory is today the foundation of reaction rate theory when you apply to calculating reaction rate constant. Inherently, the RRKM theory is consistent with transition state theory, except for transition state theory is a canonical theory. It does not consider the local energy dependency of the rate constant. But intrinsically, if you consider RRKM theory, you take an integral over the entire Boltzmann energy distribution. What you naturally should have is the transition state theory. Okay? If I have time, I'll prove that. The RRKM theory is due to Rice, Ransperger, Castle, and that was developed earlier, but wasn't that useful until Marcus, Rudy Marcus, in 1952, rigorously demonstrated how this microcanonical rate constant may be computed and utilized to determine the thermal rate constant, which, by the way, Rudy Marcus is still alive. And the other part of the work that he did was the electron transfer reaction. All right? He got his Nobel Prize for electron transfer reaction, not for the RRKM theory, that it fundamentally impacted us as far as combustion chemistry is concerned. In this RRKM theory, that's Marcus's contribution at the end. The fundamental assumption A is ergodicity. That is, vibration energy are randomized, and it shall randomize infinitely fast. If you kick into one atom into a giant molecule, then this transferring this collision energy into vibration energy. This vibration energy shall randomize itself instantaneously in comparison to reaction time scale. It's a reasonably good assumption because if you recall, the typical time scale for one outbound oscillation is around hundreds of femtoseconds. Yet collision occurs roughly every picosecond. And for reaction to take place, that's typically microsecond. Therefore, within each reaction, possible reaction scale you consider, vibration is infinitely fast. Alrighty? So you see from there, what Marcus said is that for an excited molecule, vibrationally excited, for it to react to form the product, it must go through an intermediate step. It's an adiabatic system, even though the total energy is conserved, you must pass through this critical configuration, having this vibrational energy in the right spot of the molecule to induce reaction. Then it follows that you have a rate constant that's energy dependent here, known as a microcanonical rate constant. This microcanonical rate constant must be related to the population you have for this configuration, given the initial population of the excited species. Are we okay with that? These are the population of a molecule having that energy level ready to jump off the cliff. This is the population of the molecule having energy that's sufficient to lift it up there to ask the question, should I jump off the cliff? Obviously, you thought about it. You said, well, I'm not going to do that. Next event most likely is that this excited molecule collided with something else and stabilized. You said, forget about it. I didn't go up to the hill. Okay? So, the other way to look at this concept is important. The rest method isn't important. So this is about a population of molecules ready to do the jump. This is molecules having kinetic energy that's enough to do the jump, but it hasn't come to the cliff yet. Okay? If that's the case, then one can construct a microcanonical, skip out this detailed statistical stuff. What you get at the end is a microcanonical rate constant expression that can be explained, despite all the statistics I did above, on physical ground. Okay, let me explain. I said that you have to have a configuration ready to do the jump. And this configuration obviously would have enough energy to go across the barrier. So W here is a sum of energy states available for you to do that. Okay? Rho is the density of state of the reactant. So out of all of these possible energy states, you ask the question, how many are able to do this jump? That's what this ratio is. The scaling factor is the Planck's constant. Alrighty? Then the sum of a state and the density of energy state. Sum of a state is you're asking how many energy states do I have total from a particular energy level. You count the ladders up to E DAC. Okay? The density of a state is within E to E plus dE. How many states do I have? That's the density. Obviously, the sum of a state is the integral of the density of the state. Okay? And then how do you utilize this? I'll skip this density of state stuff. Now, suppose you have some qualitative idea about this microcanonical rate constant. How do you apply this problem to a unimolecular dissociation? We'll come back to some of the theory later. Let's try to understand this thing from the standpoint of reaction dynamics. Suppose I have a molecule defined as A and AB. I shall break the A and B bond. The first step must happen is you must excite the AB molecule into something that has a given energy level E. That's E is the internal vibration energy. Most likely, this molecule excited is going to collide with something else with a frequency equal to omega, regenerating the lower-lying energy state, reverting itself back to the lower-lying energy state. But if you have this thing before this collision takes place, if everything is right, you're going to get a finite frequency for this AB star to transform itself to a molecule that is ready to do the jump. And then beyond that, you'll dissociate. So in this case, you are doing constantly excitation, de-excitation, excitation, de-excitation for unimolecular reaction. And occasionally, you get enough time to go across the cliffs and whoa. and you do the jump. Okay? Now, what is this omega? This omega is basically defined by collision rate. Okay? You take the collision rate constant multiplied by the total molar density of the gas in the system, which incidentally is pressure dependent. Okay? It's directly proportional to pressure by ideal gas law. Take this expression now, do steady state analysis on excited molecule at a given energy level. You'll get this expression. All right? And then the excitation rate divided by the stabilization rate itself is a Boltzmann energy distribution itself. I'm exciting this molecule into energy E to E plus dE, a small energy spacing. Divided by the total stabilization rate is the Boltzmann energy distribution that's called a PE. It's a probability density function. Okay? And then if you expand this term, you have the density of energy state of the molecule multiplied by the exponential function of that energy level divided by a molecular partition function that we talked about earlier. Okay? So this ratio is equivalent to the Boltzmann energy distribution we talked about earlier. Now you then ask, what is the unimolecular reaction rate constant? Unimolecular rate constant, it's a thermal rate constant. All right? It's dependent on temperature and pressure. And all what it requires is you integrate this expression. The origin of a PE comes over here. The KE comes from over here. You replace this whole thing, dk omega, by PE. What you naturally get is this expression. So the the thermal rate constant is an integral of this starting from the energy barrier all the way to infinite energy. So when you look at this, the bottom term tells you that there are two outcomes. One is be restabilized. The other is a reaction. Okay? Now you have two events going on. Only one of them will lead to chemical reaction. So you have one event that's the KE divided by sum of two events. The ratio multiplied by Boltzmann energy distribution will give you the thermal rate constant. Darn. I'm trying to do this, and in a short time, it doesn't work. Any questions here? I don't have to go on. I have a lot more down below. I know this is stuff we usually don't cover in any combustion class. Give me some feedback here.
It's a little dense.
I'm sorry?
It's a little dense.
It's a little dense, okay. All right, I'll tell you what. Let's skip all this rest of the part. If you're interested in it, you'll naturally pick it up, and this will serve as a starting point. If you're not going to do this for a living, what I think is you have more than enough you need to know for the reaction rate constant. So let me wrap this up. Going down, 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 down. All the way to the end, I just want to tell you one thing that's important. All right. Given that, how do you parameterize it? Okay. Let me go up, but you don't have to turn your page when I'm turning it. Okay. Let me get back to the part that you're interested in. So, for unimolecular reaction, how do you express the rate constant and parameter its temperature pressure dependency? in a reaction mechanism or in a reaction model. Okay. The original Lindemann expression says you only need to know the high pressure limit and the low pressure limit. In between, you interpolate it. You interpolate it based on that expression, depending on which term is important. That is, based on this expression. This is a typical form we often use to allow the slowest process to win. Okay? So the temperature dependency comes from both rate constant, the low pressure limit and the high pressure limit. The pressure dependence comes from the fact that the low pressure rate constant is directly proportional to molar concentration of the gas. Therefore, it's directly proportional to pressure. Okay? If you use this Lindemann expression, you just needed a high pressure limit rate expression and low pressure, high pressure rate expression and low pressure rate expression. Now, this additional fall off, that's called the broadening of fall off, has to be accounted for. So the way we do that is we multiply this whole thing now by some temperature and a pressure dependent factor. Now, if you take this curve divided by that curve, you know that at infinitely high pressure, these two curves must merge with each other. High pressure limit and high pressure limit rate constant. When you get a high pressure limit rate constant, all this fall off behavior disappears. When you go to the very low pressure limit, that's the same thing. The deviation occurs only in this pressure fall off region. So if you take the ratio of these two curves, the nature of this f function is that a bell-shaped curve with unity being down here. Okay? And inside is where this pressure fall-off region is. Now, fundamentally, each reaction shall have its own broadening factor. That's this F factor. It can be tall, it can be short, it can be wide, it can be narrow. It all is determined by the dynamics, the detailed dynamics of the reaction. So practically, it becomes a problem to represent it. And the way how we do that is the following. Okay. In Chapman-Enskog code, we express the ratio of this unimolecular reaction rate constant beyond the Lindemann. Its temperature and pressure dependency, we express this by taking this ratio with the unimolecular, and high pressure limit rate constant. Okay? Obviously, this value must be smaller than the unity. You cannot exceed the high pressure limit. So if I take the original Lindemann expression, divide both sides by the high pressure limit rate constant, I'll get this expression. Now in this expression, I have essentially the ratio of low pressure limit rate constant and high pressure limit rate constant. The ratio shall give you the units of what? Molar concentration, mole per cc. Okay? Is it mole per cc? No, that doesn't make sense. This ought to be unitless, sorry. No, this ought to be unitless because you're adding to 1. Anyhow. So then this correction after F is going to be expressed as a function of a temperature and pressure. Okay? This part is the Lindemann expression. This part is this curve. We have to multiply the fall-off curve, Lindemann fall-off fall off curve too to get an actual fall off. Now, usually this ratio is known as the reduced pressure. The reduced pressure is exactly the ratio of low pressure laminar rate constant and the high pressure laminar rate constant right at the middle of the fall off. In other words, the actual rate constant, you have the low pressure limit, you have the high pressure limit, you have the actual rate constant. This ratio is basically that point. Okay? That's the central point. That's the. Now you have this F factor you have to worry about. All right? We parameterize this F factor as something called the central broadening factor, FC, raised to the power of x. The remaining, this part and that part is purely empirical. And it was invented by Eugen Choi. And he said, well, this can be X factor, can be parameterized by a couple of constants. C and D are all constants. Then log PR, where PR is the reduced pressure. In doing so, you will get an parameterized form of the F factor that is dependent only on this ratio and the actual pressure itself, of course. I'm not doing this right this morning, but never mind. And this FC, this couple of parameters in this expression, the C and an N and a D. The C is related to something called the central broadening factor, F sub C, which is a function of the temperature only. And you have the N and a D, and after you take all this, you realize that there's only one parameter that needs to be determined. That's the FC, central broadening factor, and that is dependent on parameterized into four parameters, the T triple star, the T single star, the T double star, and you have another A factor. Those are four parameters, all what you need to describe the fall-off factor, provided that you know the low pressure and high pressure limit constant, rate constant. Yeah, go ahead.
Does the parameterization have any physical consequence, or is it too the form of the parameterization?
The form of parameterization initially is based on a physical consideration for very simple unimolecular dissociation reaction. Okay, and that has been tested for simple unimolecular reaction. Today, we are just using this parameterization for any reaction. Okay, after all, this is just one format. There are Chebyshev polynomial approach. There are many other approaches. This remains to be an active area for modifying ChemKing to accommodate for various types of pressure dependency calculation. Okay, but overall, since each reaction shall have its own broadening behavior, to parameterize this whole thing so that you can accommodate for a theoretical calculation, all right, that it may involve many reactions will always require approximation. Okay. Now, with this parameterization, that explains many of the things you found in the unimolecular reaction. I talked about this yesterday. For hydrogen recombination with a hydrogen, methyl recombination with the hydrogen atom, produce methane. This is what you typically see in many of the reaction mechanisms. The first row on the same line as the reaction expression, those are A and E for high pressure limit rate constant. The next line with a low in the front is the low pressure rate constant, that K0. The next you'll find the four parameters. This is A triple star, a single star, a double star. Don't ask me why you have to organize this way. This is just the convention. The triple star, the double star, the A single star has no physical meaning whatsoever, so it doesn't matter. Okay? Be really careful with that. And this then is followed, of course. Those parameterized value goes into this expression to calculate F sub C for a given temperature. F sub C got plugged into the expression for those C and N. So at a given temperature, you will get value for C, N, and D. You then take values of a C, N, and D, plug into this function, where C and N, I believe, are dependent on temperature. Then you have this log of reduced pressure calculated based on values you determine at a given temperature and pressure for low pressure rate constant and high pressure rate constant. Okay? Then you have everything you know. You calculated X. FC has already been determined. All right? Then you determine the F, put it there. You determine now the ratio of unimolecular rate constant at temperature and pressure. You know the high pressure limit rate constant value at that T, you get a unimolecular rate constant. So it's a very long way to get to this KPT dependency. Can you do better? Why this has to be the standard? For that matter, why do we have to use Arrhenius law to begin with? Do you all know that in computation, evaluating exponential function is very expensive, right? Why can't you parameterize into some sort of polynomial? In any case, I said that Arrhenius law, there's no physical basis why rate constant must be expressed by the Arrhenius law. It's empirical. If that's so, why bother? Why don't you just fit everything in polynomial form? You bypass the exponential evaluation. Many things we do is because of a tradition. Once you have this tradition, it's so hard to get away from it. But then starting from thermochemical property I talked about on Monday, all the way to rate constant expression, if today, without all this tradition, you're going to start over again, I'm very sure you all do this thing very differently. Would you agree? So anyhow, so these are all the significance of these parameters. And then you have the Chapman efficiency for dominant chemical species in a typical combustion problem, and that is multiplied to the low pressure limit rate constant, and multiplied to low pressure rate constant only. It is only for the low pressure limit that you have those impact of different species leading to different rates of collisional excitation and de-excitation.
If you have a gas mixture, how do you average the impact of the different constituents?
So let's suppose you have 3 gas, tri-component gas. Let's say this is A, B, and C. Suppose your relative, this whole thing, the Chapman efficiency to A. So by definition, A is 1. It's relative to itself. Let's say B is twice more or better collider than A. C is 4 times better or collider than A. Then the low pressure limited rate constant is basically equal to the original K uni 0 multiplied by concentration of A multiplied by 2 times the concentration of B multiplied plus 4 times the concentration of C. It's not because concentration got doubled or quadrupled. It's because the unimolecular reaction rate constant got doubled and quadrupled. Okay? That's how you do the averaging, if any. All right. I'm done for the day. Didn't go very well. Proved that I can do quantum mechanics and statistical mechanics in one day, but I can't do transition state theory and RRKM theory in one sitting. So